Hello, my name is Ilum Lesher. I'm an undergrad at Grinnell College in Iowa. I study physics, and for the last year, I've been researching computational astrophysics with a group first based at MIT and the University of Virginia, and now here at UF through this REU with Deshka Narayanan's group, also closely mentored by Drew Zimmerman. A little bit about myself. I'm an avid enjoyer of the outdoor world. As you can see in these pictures on the left, it's me in a variety of exotic locations along the globe. I'm very passionate about physics as well. I'm trying to find a way to kind of merge the two. So if anyone has any unique ideas about how to do physics in the outdoor world, please let me know. That'd be great. My project this summer has been looking to answer the question, how well do we know dust mass in high redshift galaxies? So to start, I would imagine that everyone in this room wants to understand the universe. And I would also imagine that everyone in this room who wants to understand the universe turn to astronomy to do that. Now, astronomy is a little like squeezing water from a rock in the sense that we have an absolutely minuscule amount of data available to us relative to the size of the universe. And from that, we have to get the most amount of information that we possibly can to get the most amount of understanding out of it, right? So needless to say, if we want to understand the universe, we have to understand the structures within it. Galaxies are, of course, a pretty typical example of a structure in the universe. And for galaxies, squeezing the rock to get the water out of it is inferring what's happening in these galaxies through observational data. Now, to this end, dust has a very significant role. It has this very annoying characteristic that it absorbs UV photons and re-emits them in the far infrared spectrum. So it literally changes the data that we have available to us. The already very small amount of data gets, even more disrupted with dust. So if we want to understand the universe, then we have to understand galaxies. And if we want to understand galaxies, then we have to know dust in the galaxies. A little more specifically, this squeezing the rock technique for galaxies is spectral energy distribution, or SED, fitting. Now, this is the technique that observers use to recover physical properties of galaxies through observational data. This technique requires certain parameters for the fitting models that have to be tuned in order to give accurate results. Now, these parameters are basically assumptions that we make about the physical nature of these galaxies. So it's actually kind of paradoxical because you have to make assumptions about physical stuff in these galaxies in order to infer the physical properties of the galaxies. A little confusing. So something that theorists will do is try to tune these parameters to give us the most accurate technique and thus the most accurate results and the most complete understanding of what's happening in the galaxies. This is exactly what my project is doing this summer. By answering the question, how well do we know dust mass in high redshift galaxies, I will get a better understanding of how well our SED fitting technique works, and then backtrack and tune some of the parameters and different choices we make for the models to give us better results. Now, we're doing this at high redshift because this is kind of the limit of our understanding. This is the limit of our abilities with SED fitting. The higher the redshift, the less accurate the results are. And so we really wanted to see just how far we can push this. So to do this, I'm using, I hope this works, I'm using galaxies from oh, that works, perfect. I'm using galaxies from a cosmological simulation suite called SIMBA. It tracks galaxy formation and evolution through many billions of years. This is a video of some like gas accretion over many different redshifts. And with these galaxies, I'm running a program called Powder Day, which pretends to be an observer in these simulations. It basically pretends to be a space telescope, or rather several space telescopes in the simulation, and then look at these simulated galaxies and produce an SED like is shown on screen for them. So in this plot, you have the SED curve in black, and then the observed photometry points in red, which correspond to different filters used by the telescopes. Again, the quote-unquote telescopes. They're not actually telescopes. So from these quote-unquote mock SEDs, you could call them, I run a program called Prospector, which goes through and then examines all of these mock SEDs, and it compares them to model SEDs. And so these model SEDs are what are tuned with the parameters I was mentioning earlier, those physics assumptions that we made. And so once it finds a good fit between a mock SED and a model SED, we can use that to infer the parameters that were used for that mock SED. So in this image, we have the same Powder Day mock SED from the previous slide in black, as well as the photometry points. And then we have in blue the Prospector fitted SED. So it will fit to the black photometry points as well as the physics parameters that we're using. And so, yeah, once we have a good fit, we can infer that the galaxy used to make this SED has a similar dust mass to that was used in the model SED. And then we can go back and compare that inferred dust mass to the actual dust mass from the simulation, which, of course, we have access to because it's a simulation, which is great. So that's what I did many, many times for a lot of different scenarios. And here are some results. So first, we've got a plot of the actual dust mass on the x-axis and the inferred on the y. This is for snapshot 305, which corresponds to redshift 0. So if this were a perfectly accurate technique, then every single point would fall along the diagonal, which, of course, you can see is not the case. In the bottom right, we have priors 1, which refers to a specific choice of parameters that were used for these models. And you can see it does pretty well for high dust masses and pretty poorly in the low dust mass regime. It's actually a lot more deviation than you'd probably expect to see at redshift 0. So it's interesting. Then we chose another setup of priors and ran the same thing. And you can see that it's actually pretty much the identical result. And if we do it a third time, it's also just about the same. So from there, we moved into higher redshifts. We have redshift 0 on the left. That's the same plot as the previous slide, then redshift 2 and redshift 6. Redshift 2 does quite well with the exception of a couple outliers, but it's got a pretty good diagonal trend there. I wish I knew how to use the laser pointer, but I'm not going to mess with it. Redshift 6, you've got a bit of like a vertical phase shift almost, but it's still got, kind of see a diagonal trend there. But what is interesting is that for all of these plots, it looks like the choice of parameters doesn't matter at all. I mean, all of the points are basically falling in the same places every time. So instead of varying the parameters, we chose to start varying the filters. Now, varying parameters might give you better results. Removing filters will never give you better results because you're removing the data that you have accessible to you. So on the left, we have an SED with a fitted SED from all of the filters that we're using originally. And then on the right, we have removed some of the far infrared and all of the mid-infrared filters. And you can see that the blue prospector fit definitely gets worse. I mean, it completely misses that last photometry point there on the right. And as you might expect, this does pretty poorly. So I want to clarify first, this is redshift 8. So we've already moved even further into the redshift. And so we're expecting worse results. And so on the left, you have before we've removed filters. RD does very poorly. I mean, we evaluate it with the R squared, which is just a pretty common metric of evaluating this sort of performance. R squareds are normally between 0 and 1, with 1 being perfectly accurate, 0 being pretty bad. -19 is completely abysmal. I mean, you can see it's a vertical line. It's terrible. And somehow it goes from completely abysmal to completely abysmal when we remove some of the filters, and it goes to R squared of -22. So clearly, as expected, removing filters makes the performance worse. So it actually did so bad that we decided we should check that our technique is actually working and doing what we'd expect. So here we've got a stellar mass test where we have on the left the original dust mass plot, and then on the right, we inferred the stellar mass. Generally speaking, we would expect that the stellar mass would do just a little better than the dust mass. And in this case, we do see that's the case. I mean, the stellar mass is still pretty bad, but R squared -9 is not -19. Granted, it's still pretty bad. But this was some sort of validation that, okay, this is at least doing something, so we expect. So this obviously is still very much in progress. But what are the conclusions? I would say takeaways that we can get from all this work. So to start, SED fitting to infer dust mass is worryingly inaccurate. Like I said in the start, understanding dust mass is very, very imperative if we want to understand what's happening in galaxies. We have to know. We have so little information that's available to us through observational techniques, and we have to understand what the uncertainties are. So, we saw in this original plot, redshift 0, I mean, it deviates so much in the low mass regime that that is worrying. I mean, like, you'd expect it to do pretty bad for redshift 8, et cetera, but like redshift 0 is kind of brutal. And this, of course, could be for, numerous reasons to do with the simulations and the choices we made, but at least this is what we're seeing here. So, if you will, I mean, it's really hard to squeeze water from a rock, basically. Also, high redshift galaxies struggle pretty bad. We saw that in the previous slide with this redshift 8 setup here. And again, this is important because in the era of James Webb Space Telescope, I mean, we're constantly observing, higher and higher redshifts, and it is definitely important to understand the systematic uncertainties that come with them. So I don't think either of these points are necessarily surprising. I don't think if you ask anyone, hey, how well can we infer dust mass at redshift 8? People are like, oh, it's extremely accurate. But again, it is important to understand where we're at and how much the uncertainties impact us. And this is also, again, in progress. You know, I've got the workflow set up. I'm starting to get some preliminary results, but now we can really make decisions to try and get some more impactful results that can really, you know, be informative to observers. So some further work could be, you know, trying to examine what filters are actually relevant, trying a bunch of different filter setups to see, oh, is this like, you know, is this something that's realistic? Will this be good for observers to know? But you know, there's a lot of different paths we can take from here, and I think it's important to do this work. I know a lot of people are working on similar stuff, even in our own group here at UF. But I think it's genuinely important to really, you know, it's not as exciting as doing the observing, but it's still necessary, I think. I've also got some example questions if you want to ask some, but I see some hands, so yeah.
The DOS model within the simulation, because that's the other thing you need to worry about. How accurate the observation are, but also how accurate is your mark.
Yeah, I mean that's definitely that's the question, right? You know, what is the dust setup that we should use? I mean, there's so much literature about different models and different parameters that you can use. I think most of these were used like the Drain and Lee 2007 model. But you know, whether you're including pause or whether, you know, you have a certain type of attenuation curve, or there's so many choices you can make. And it varies a lot. All of these, excuse me, some of the different prior setups had different dust models and engaged and et cetera. So, but yeah, that is the question. Yeah.
What were you exactly like? Was it the parameters or like the boundaries?
It was parameters. Well, yeah. It was kind of both. So we were adding different parameters as well as adjusting the range of the priors. So, you know, I fortunately don't have a slide for all the different choices we made, but there was a lot of choices that were made. Yes.
Probably one.
Filters you showed presumably were motivated by something people were actually using. So can you say from what you were doing here that people are systematically overestimating galaxies at redshift 6 and 8?
I would love to say that. Well, okay, I wouldn't love to say that. As far as physics or, you know, actual results go, I would love to say that. But it's going to take a lot more testing. You know, these are, again, preliminary tests, and we use for the remove filters, we use all of the James Webb filters and then one Herschel in the far infrared. You know, it's going to take a lot of different testing with a whole bunch of setups to really evaluate, okay, is this, you know, well, to just evaluate the significance of all of it. But that's the goal. That's the goal. All right. Thank you.